Swayam Prabha. Digital India. Educated India.
Manoj Harbula gave a very eloquent summary of quantum mechanics. But you all know that quantum mechanics, what he discussed, deals with Hermitian Hamiltonians. And therefore, the evolution is unitary. Now, in reality, of course, often we come across non-unitary evolution because of quantum dissipation. So the ideas that I'm going to convey, hopefully to you in the next 20-25 minutes, is very similar to what happened in Brownian motion. Remember, Robert Brown was looking at a ball going down a jar of water, and then he found that the ball was undergoing random zigzag motion, and it took the world about 80 years before Einstein in 1905 gave a kind of a phenomenological theory of the Brownian motion, where he said that, well, as the ball goes down, of course it goes down by gravity, and there is also Archimedes' principle, but the ball is also being randomly kicked by the surrounding water molecules, which are much smaller in size, and they cause a frictional effect, which gives rise to a force opposing the direction of the ball motion. And that is where we learned how to calculate, how to determine viscosity of a liquid. So now you apply this idea to quantum mechanics. So your Brownian ball is now a quantum particle or a quantum subsystem, we'll call it. And then the surrounding system is also often quantum mechanical. And this is an idea of what is called an open quantum system in a subject called dissipative quantum mechanics. Here, we'll take a slightly different approach, very akin to the Brownian motion approach, where the effect of the surroundings is taken into account through random kicks. So I'll explain that to you. So, right. Now, you know also that if I have a unitary evolution and I interrupt that evolution at regular intervals of time, then there is what is called wave function collapse. This was long discovered by two Indian scientists, Baidyanath Mishra and ECG Sudarshan, called the Zeno effect and the Zeno paradox. And now what we would like to do, however, is not kick the system at regular intervals of time, but random kicks. Randomly lath maros. So this is what we'd like to do. Because our experimental colleagues in Italy say that this is more amenable to experimental situations. So why does this question matter? This question is important. I'm just giving you some references. In Quantum Measurement and Projective Trajectories, there's a book by Wiseman and Milburn and Jacobs also. Then Gardiner and Zola, a book on quantum optics. Incidentally, quantum mechanics manifests in our world mostly through electrons and photons. Now, photonics, of course, are important in quantum optics. I'm not going to discuss that. But electrons are, of course, very important in chemical physics and also in solid-state physics, and that is our focus of attention. Then there is a new development thanks to some work by actually another Indian scientist now living in France for many years. He earlier worked in the Tata Institute, Satyam Majumdar, called quantum resetting. And then, of course, many of you here are familiar with relaxation phenomena in NMR, EPR, etc. And this kind of work was done long ago by Rigo Kubo of Japan in 1969 onwards. So what is our model? Our model is you start out with an explicitly time-dependent Hamiltonian where you have a system part which is given by H0, and then you have a time-dependent part. We have an operator Vi, which does not necessarily commute with H0, but the pulses are assumed to be delta functions in time. This is an assumption. You can play around with that assumption. But if you assume a Poisson distribution for the pulses with a rate, which I will define, well, it's given in the next slide, then you are in the Markovian limit. Now, there's a connection between this and also the open quantum system approach that I just mentioned, where you take the heat bath, the external surroundings, to a very large system, and then you go to this so-called Markovian limit again, where correlation functions are taken to be very short-lived, and so that I will not go into now. So I think I have explained all these terms, and now, all right, just to give you an example of what can be H0. Take a simple spin half case, and here H0 exists in multiple, H0 has two terms which do not commute with each other. It has a sigma z term and a sigma x term. So imagine that you have a magnetic field along the z-axis and you have a transverse field along the x-axis, somewhat similar to NMR geometry where the frequency is taken to be 0. And now if you calculate what is the, starting with a spin in a given state, let's say the -1 state, what is the probability of finding it in the plus state? And this is given by equation 3. And this is a very familiar Rabi oscillations. So now you can ask the question, what will happen to Rabi oscillations? Of course, would give you a coherent evolution. And you'll ask the question, what happens if you randomly pulse this system? And so these random pulses in the context of magnetic resonance could happen because if the spin system is interrupted by the external phonons and things like that. All right. Now, so coming back to Manoj's talk, remember he was talking also about Einstein AB coefficients and all that, transition from one state to the other, and then induced emission and all that. But see, if you have a Hermitian Hamiltonian, then transition probability from one state to another state is the same as the reverse transition because time reversal is maintained. Now, in nature, we see violation of time reversal invariance in this context in two different situations. Suppose you have temperature. Then you have to bring in statistical mechanics. So you have to have different populations of the excited state and the ground state. And these two transition probabilities are related by what is called the detail balance. Furthermore, what happens when there's a line width? This is something that is brushed aside in our quantum mechanics course, and the width is just put in by hand. But in order to calculate the width, you have to go beyond quantum mechanics and do quantum field theory, where you have to connect the system to a quantum Hamiltonian for the surrounding electromagnetic field. So therefore, this is an interesting and important question to ask in this context as well. So it's a pictorial demonstration of what I just now said. You start out with the density operator. I'm going a little technical now with your permission. A density operator at time t equal to 0. And at times t1, t2, t3, you give random jolts. Okay? And these are assumed to be delta functions in time, so that what happens is, so in between two pulses, you have one form of the Hamiltonian, which is H0 plus V1, and then suddenly it changes to H0 plus V2, and so on and so forth. And then you assume that these pulses are governed by a Poisson distribution. Okay. Another example of your subsystem would be a coupled Hilbert space, where very simple model is a hyperfine interaction. The simplest case of a hyperfine interaction, where the A is taken to be a constant, which is a coupling constant, and Iz is a Z component of the nuclear spin, and Sz is the Z component of the electronic spin. I'm assuming each is equal to half. And here is a schematic description on the right-hand side. So you have a probe nucleus. Either you can do NMR, or you can do Musbauer, or whatever, or perturbed angular correlations. And then your nucleus is coupled to the spin system, surrounding spin system. The surrounding electronic system sees more of the external bath effects through either spin-spin relaxation, what are called T2 relaxation processes, or spin phonon effects called the T1 relaxation processes. So it's an example of a coupled Hilbert space. The point I'm making is your H0 can be quite complicated and can actually live in multiple Hilbert spaces. At the TIs are all randomly distributed, and the probability that S pulses occur in time t, Manoj, thank you for asking me, is given by lambda t raised to the power S over S factorial e to the power minus lambda t. So you are bringing in a phenomenological parameter called lambda, which you call relaxation rate. It will be microscopically related to some correlation functions in the Bath variables. Yes, indeed. Indeed. We have worked on that. So what he's asking is, suppose you have an Ising model and you have also a transverse term, then you have now another field parameter, which is a transverse field in addition to the temperature. And as a function of the transverse field, you have a quantum phase transition. And now you can ask the question, what happens when you have dissipation in that system? All right, I think I have already dealt with this slide. And the last equation 5 is what I mentioned to Manoj. Manoj is now talking to Pratim Chattaraj. Okay, so here is a bit of a technicality. Well, everybody knows. So because your Hamiltonian is actually doesn't commute with itself at different times, so you need time ordering. And your rho of t is given by equation 6. And now you have to do an averaging. You have to do an averaging over the pulse distribution in this case. It's tantamount to averaging over the Bath variables. Now, when you do averaging, you have one time-ordered series on the left-hand side, another time-ordered series on the right-hand side, and that's complicated. So a way out is to enlarge your Hilbert space and go to what is called a Liouville space. And on this, actually, a lot of people from chemistry departments have worked, starting with Hugo Fano in Chicago, and then Ben Reuven and his student Abraham Nitzan in Tel Aviv University. So you write it as a Liouville operator, and here is a mistake. You know, I am digitally challenged person. So these slides are done by some student either in Bhubaneswar or in Chandigarh or in Bombay. So it's usually written with an H cross. Cross is in the superscript. Here it is written as a subscript. But the H cross A, that is a Liouville operator associated with the Hamiltonian, operating on an ordinary operator, gives you the commutator of Hamiltonian with that operator. There could be IH bar terms, etc., which I think I have not included there. So, the name Liouville is associated because he did it for Poisson bracket, and then people like Kubo generalized it to quantum mechanics. So, all right. So, therefore, you need a transition operator. Now, one point you should note that, see, normally Schrödinger evolution occurs as like e to the minus iht. Here is a time-dependent Hamiltonian, so you need an integral. When you integrate, when the pulse occurs, it's a delta function pulse. So during that time, the subsystem doesn't make any contribution because h0 t and the limit of t going to 0 will not contribute. But the delta function term does. And so the VI term, now VI cross, because it's a Liouvillean, will show up here. And so I have a transition operator. And so and now you have to do an averaging over the transition operator. There are two kinds of averaging. One is the averaging over the pulse distribution, as I mentioned, over a Poisson distribution, and also an averaging over the strength of the pulses. So you can either model this VI directly, which is useful in T1, T2 processes, or model the average of T directly, which is useful in quantum measurement and resetting, which I'll indicate. So now I go into a little bit of mathematical analysis, but let me tell you physically the idea. So the way you set up the problem is that you have n pulses. Of course, each pulse, as Manoj was saying, each pulse is distributed at random. You don't know when they'll occur. Even if you say that there is no pulse, you have to assign a probability. What is the probability that no pulse occurs? Is it simply exponential minus lambda t. No pulse occurs in time t. Because, Ps of t is lambda t raised to the power s over s factorial e to the minus lambda t. So if s is 0, you simply get e to the minus lambda t. That's the probability. So you first ask the question, what happens in time 0 to t if there is no pulse? Then ask the question, what happens when there is one pulse? Then you evolve from time 0 to t1. At t1, you give a jolt. And then from t1 to t, again you evolve. And then you calculate what is the transition. So you write the density operator starting with a row of 0 and then go into row of t. 2 pulses, 3 pulses, n pulses, you sum, then you average over a Poisson distribution. And this equation is actually an infinite series, which you can handle easily by taking a Laplace transform. And when you take the Laplace transform, you get what Kubo called a stochastic Liouville equation. So I will not go into the mathematical details, but this is the stochastic Liouville equation given by equation 11, where rho s average, s is the Laplace transform variable, the average is given as here, where the propagator gs inverse has a width acquired already, added to the Laplace transform variable s with a subsystem Hamiltonian H0 cross, and then you have the transition, all the masalas, all the happenings are here occurring through the lambda t term. So let me also make some connections. Sorry. Yeah. So suppose you assume that the pulses give you weak pulses. The strength of VI is small. Then you can do a perturbation theory. And if you do a perturbation theory, just to make it familiar to you people, that you get an equation for ddt of rho of t average, which has the form of a master equation, which is known as the Gorini-Kosakowski-Lindblad-Sudarshan master equation in the weak coupling approximation. So there are various limits that you can look at. So some time ago, Divira Sehgal, I think also in chemistry department in Toronto, and her students did some work in a different method using the master equation approach. a student of Shamik Gupta, who is now in ICTP Trieste, and myself, we did some work using our method, and I'll just quickly show you the results. So 1 minute each for the examples. So simple system, the first example that I gave you, your subsystem is AIZSZ. Take each nuclear spin, electronic spin to be 1/2. And now you make a transition between the nuclear spin levels like you do in NMR. And so you have the transition between the states 1 and 2, and with a gap of delta. The question that Segal et al. Asked is that what happens when you have nearly degenerate states? The delta is very, very small. And question, therefore, is can you generate a very slow relaxation which will maintain coherence? Because that is, of course, your objective for information, quantum computing, everything. So this is using our method. Let me not go into the details. In fact, we found exactly the same answer as Segal et al., where the diagonal elements of the density operator and also the off-diagonal elements exhibit a term which has a time scale given by, one is the very fast time scale because lambda is very large, tau, they go down exponentially, but the other time scale is lambda over delta square. So if you have nearly degenerate states, then delta is very small and lambda can be large, and so tau 2 can be very small. You can tune tau 2, and you can tune the system to maintain coherence, and that is an objective. It's another example that they looked at is a 3-level case, which we put it in our language. Think of a quadrupolar kind of interaction where you have a hyperfine coupling IZSZ, but the electronic spin is not spin half, but a spin 1. So you have a quadrupolar interaction given by 3sz squared minus s squared with a quadrupolar coupling constant Q. So now you have a 3-level system, and therefore now you have to introduce detail balance with the temperature effects, and those temperature effects are put in through the transition probabilities that you build in through the transition operators T that you mentioned. I have to go a little fast here because Raj is giving me signals. So the steady state solution satisfies both normalization and thermal equilibrium constraints. So this is the detail balance relationship, and the W matrix takes care of that. Now, right. And this is an unusual 3-level case that we just published with Shamik Gupta, who is in Tata Institute, is a 3-level case where the levels 1 and 2 are coherently coupled, the first two terms, E, epsilon, and delta. But then the level 2 is incoherently coupled to another level 3. The level 3 is being pumped into by a delta function pulse following our methodology. So this is analogous to how a laser works, except in laser, the third level, it coherently pumps the other level, and you have population inversion. Here, we don't take into account any temperature effects or detail balance, but it turns out that you can actually, if you don't have that random pulsing, you can connect it to the Rabi model that I mentioned at the beginning, and which you must be all familiar with. And so the population of level 1, starting from saturation, gradually decoheres to 0 through leakage to level 2. So again, I don't want to go into any details here. We generated graphs here. This is something I must talk about because in 2022, we also wrote a few papers. The first one, and here is our Sati who comes in. He was the editor of Resonance, and during his editorship, I probably contributed 7 papers in Resonance. It was great fun because with the editor and the author, there was this symbiotic relationship where the editor will also contribute to my articles. So much so that he actually drew the pictures for graphene orbital for carbon, sp2 orbitals for me as an editor. Once he has left, well, I have only one paper which Rajarshi knows about recently, so this was the first paper on a tight binding chain. A tight binding chain is something that we all learn in elementary solid-state physics, that you think of your lattice as an infinite lattice. Think of a chain. This can be applied to a carbon nano chain, and you assume that the electronic states are mostly localized at the nuclear sites, and occasionally the electron hops or tunnels from one side to the other. This is something that goes back to Felix Bloch, and you can actually solve the problem exactly. And what we did is to now take the subsystem as a tight binding chain model, the subsystem Hamiltonian, and you say that what happens if you randomly kick them? The evolution. So you start with a given site and then randomly kick, but then you do also a resetting, which is what Satya Majumdar and Evans from Scotland, Edinburgh were doing. And so resetting means that you pick up a site, capital N, and I'll define what is resetting, or you do a quantum measurement at the site, capital N. So we wrote some more papers in Journal of Statistical Mechanics. And so here is a small introduction to the tight binding model. You have a K dagger. K takes you from site M to M plus 1. K dagger does the opposite. And they're like the annihilation and creation operators, except that here they commute. So that makes the mathematics much simpler. And you can write down what is the probability of finding the particle at the mth site is a Bessel function of something squared. And you calculate the mean squared displacement. It is somewhat like a free particle relationship, delta t squared over 2. So you have ballistic evolution, and you ask the question, what happens when ballistic evolution is interrupted randomly? So you can do quantum resetting, which is defined by equation 32 by the T matrix that I had given. Actually, again, my student mixed it up, and as I said, I did not know how to correct it. It should be T cross, the superscript, because it's a Liouvillean anyway. So, or you think of T as a super operator. So you need 4 indices to define the matrix elements. And so quantum resetting means that you have classicality, that is, you have delta function between n and n prime, m and m prime, and the final state n, little n, is the same as capital N, where you reset. So we did that. Then you can do also quantum measurement, where the final and the initial states are also the state n. And so it is called a projective measurement at site n, collapsing the wave function locally while maintaining coherence elsewhere. So here's some numerical results where you ask the question, suppose you start from the first site and ask the question, what is the average probability of finding the particle at the 5th site? And so, or the 10th site, and you can see a difference between the 2 graphs showing that the coherence eventually dies out, and the numerical and analytical results agree very nicely. Then you can also look at the behavior of this function as a function of the rate lambda, which is like a relaxation rate with an increase of lambda or a decrease in the time gap between 2 successive resets. The particle is more likely to be found in the neighborhood of the detector site, capital N. I think I've run out of time, and so I will stop here. But here are the core ideas which you can read out from the last slide. Thank you so much.
Swayam Prabha. Digital India. Educated India.